Welcome. In today's video, we're going to derive the characteristic function of the gamma distribution. Recall that if x has a gamma distribution with, say, parameters alpha and beta, then the PDF, or the probability density function of x, is given by the following. Fx of x is equal to beta to the alpha all over the gamma function evaluated at alpha, x to the power of alpha minus 1, e to the negative beta x, where x is greater than or equal to 0. Notice that this gamma function here is given by the following definition, and I might write it as this. It's equal to the integral of 0 to infinity of e to the negative x to the power of alpha minus 1 dx. And we know that this function actually simplifies simply to alpha minus 1 factorial when a is an element of the natural numbers. So, without further ado, we can now derive the characteristic function of the gamma distribution. And that characteristic function is going to look like something like this. Var phi x of t is equal to the expected value of e to the itx by definition of what the characteristic function is. Now, a gamma distribution is a continuous distribution, so therefore we're going to use the continuous version of expectation. So we integrate across all values of x on the support of x across eitx multiplied by the probability density function with respect, and then integrate with respect to x. Our next stage is to simply substitute some of our numbers in. So we know that the support of x, for example, is for any x greater than 0. So our terminals now go from 0 to infinity. We still have our e to the itx here. And now we're going to multiply by the PDF of the gamma distribution. So I'm just going to write it down here. X to the alpha minus 1. E to the negative beta x dx. Following on from this, what we're kind of trying to do here is simplify our expression. So notice that one element of simplification here is to combine this exponential term at the front and this exponential term at the back. So that's exactly what we're going to do. So I'm going to write 0 to infinity of beta to the alpha on gamma of alpha, x to the alpha minus 1, and then I'm going to write this as e to the negative. Now I'm going to be a little bit clever here, and instead of writing it in the way you'd suspect, I'm actually going to write it like this. So I sort of have this, I conserve this negative something times x. Instead of just having plus it, I'm trying to conserve this negative factor times x here. And in fact, what we will do here, and the reason I'm going to do this is because now what I can do is I can say, well, I'm going to define this new variable s, which is equal to beta minus it. Similar to the case where we were deriving the moment generating function, I'm going to try and do something similar here. So, if I do that, then what I'm going to do is I'm going to cleverly just put the beta alpha at the front here. I'm going to take it out the front, beta to the alpha. I'm going to rewrite my expression here, alpha x to the alpha minus 1 e to the negative sx dx. And I'm going to put in a particular expression at the top here, s to the alpha, and then I'm going to divide by s to the alpha outside the integral. So theoretically, these two would cancel, and you get back to the original item above, or the line above. So keeping that in mind, why have I done this? Well, the trick here was to establish a new parameter s, replace that value of s here in the probability density function, and what you'll notice now is that the expression here, by placing an s cleverly here and then dividing by it, we have an expression which looks exactly like the gamma distribution altogether. And we typically say that the component dependent on x of the distribution is called the kernel. And then here we have a component which is independent of x, and that's sort of a multiplicative factor that we use. And so cleverly I've sort of forced the multiplicative factor here to look like it is the gamma distribution. Now, one important property of a PDF, or a probability density function, is that when you integrate a probability density function across all of its support, in this case 0 to infinity, we end up with 1 by virtue of the fact that it's a probability distribution function. So in fact, what now we arrive at is beta on alpha. This s to the alpha I'm going to replace again with my original beta minus it, all to the power of alpha, and we know that this simply multiplies to 1, this whole integral expression, because it's the integral of a PDF. Given that now, we can do a bit more of a simplification. We can bring the power out of this fraction expression, so that gives us beta on beta minus it to the power of alpha. And finally, we can just simplify it a little bit and say that it is equal to, if we take the reciprocal of what's inside the brackets, we can say that's beta minus it on beta, but now to the power of negative alpha. And then furthermore, we can do a division here of our fraction and simplify this a little bit further, giving 1 minus it on beta to the power of negative alpha. And there you have it. Here is our expression for the characteristic function of a gamma distribution. I hope that was informative, and hope to see you in the next video.